Good evening, sir. You can start now, sir.
Okay, ma'am. Thank you so much. Good evening, students. Last weekend, I gave you a test on electromagnetic induction consisting of 25 multiple choice questions. In this class, I am going to discuss the solutions for the numerical problems. So, I will be sharing my screen with you so that we can quickly discuss the solutions for the multiple choice questions. Are you able to see my screen, students? Students, can you see my screen?
Yes, sir. Yes, sir.
Okay. This was the first question you are seeing on screen. A rectangular, a square, a circular, and an elliptical loop, all in the xy plane, are moving out of the uniform magnetic field with a constant velocity v, vector v equal to v I cap. The magnetic field is directed along the negative z direction, z-axis direction. The induced EMF during the passage of these loops out of the field region will not remain constant for. You are having four options. So what they are telling is they are having loops of different shapes here: a rectangular, a square, a circular, and an elliptical loop, all in the xy plane. They are moving out of the uniform magnetic field with a constant velocity vector v equal to v I cap. That means those loops are actually moving along the x-axis. Okay, so those loops, all the loops, four loops, rectangular, square, circular, and elliptical loops, all move in the x-axis with this velocity vector v. And the magnetic field is directed along the negative z-axis direction. Okay. So the magnetic field is along negative z-axis direction. The induced EMF during the passage of these loops out of the field region will not remain constant. When these loops move, actually they are actually moving in the region of the uniform magnetic field directed along the negative z direction. So when these loops move, EMF is induced on all the loops, okay, due to the change of magnetic field linked with the loops. So what will happen to the induced EMF? That will not remain constant for, okay, for these loops. Okay, so you need to find out the correct option among the four. Okay, so here you see, we know very well that EMF E equal to minus d phi by dt. So here minus d phi by dt means phi is actually equal to b into a, that you know very well. Magnetic field into area. Here the magnetic field is constant. So from phi you can take the magnetic field outside the differentiation, and here dA by dt is the variable, because when the loops actually move away from the magnetic field, okay, the area which is in contact with the magnetic field, or the area through which the magnetic field passes, it changes actually. So that is dA by dt. So E equal to minus d phi by dt, that is equal to minus b into dA by dt. So here the area is the only variable. So the change in area with respect to time, okay, so that thing actually is not constant for elliptical and circular loops. Okay, for elliptical and circular loops, when they move along the x-axis, okay, what happens is the area covered, that is not constant for loops of these shapes, that is elliptical and circular loops. So what happens is the induced EMF will not remain constant for both these loops. Okay, so for circular and elliptical loops, the area that through which the magnetic field passes, that is not constant. So that's why the EMF is also not constant. So that means option B is the right answer, that is the circular and the elliptical loops. So this is how you need to understand the solution for this problem. The second thing is, the second problem is, a conducting circular loop is placed in a uniform magnetic field 0.04 Tesla with its plane perpendicular to the magnetic field. The radius of the loop starts shrinking at 2 millimeters per second. the induced EMF in the loop when the radius is 2 centimeter is. So here you are having a conducting circular loop that is placed in a uniform magnetic field, and they have given you the field value also 0.04 Tesla. The circular loop is placed in the field such that its plane is perpendicular to the magnetic field. So plane is perpendicular to the magnetic field means you can get maximum flux through the circular loop. Okay, when the plane is perpendicular, what you can see is the angle between the magnetic field and the area vector is 0 degree. So that means the flux linkage with the circular loop is actually maximum. Okay, so now we have to find out the induced EMF in the loop when the radius is 2 centimeter. So why they are asking us to find out the induced EMF at a particular value of radius? Because the radius of the circular loop is actually shrinking. Okay, it is shrinking at 2 millimeter per second. So the radius of the circular loop is not constant and it is shrinking. That means at a particular value of the radius, that is 2 centimeter, you need to find out the induced EMF. So you have 4 options and you need to find out the induced EMF. So for that, once again, you need to apply this formula, E equal to minus d phi by dt. Okay, E equal to minus d phi by dt. Here also the magnetic field is constant, so I am taking it outside. dA by dt means change in area with respect to time. For a circular loop, the area is given by this term pi r square. Okay. Once again, here pi is a constant, and what you can do is you can take pi outside. Okay, and this r squared is the only variable because the radius is shrinking at some rate. Okay, they have given in the question itself. So the radius is shrinking at a particular rate. So when you differentiate r squared with respect to time, you will be getting 2r into dr by dt. Okay. So then what you have to do is you have to find out the EMF at 2 centimeter radius. So here you see EMF, for the EMF you have all the values. Okay. So from this equation, what you can do, you can substitute all the known values and you can find the EMF. So here you can see minus b into pi into 2r into dr by dt. Okay. So here that r is 0.04 meter. So into pi is 3.14. Actually, we don't have to substitute the value of pi because in all the options you have the value of pi kept as such. Okay. So it is not required to substitute the value of pi here. So minus 0.04 into pi into 2 into r. R is 2 centimeter, that is 2 into 10 power minus 2 meter into dr by dt. dr by dt means the rate of change of radius. It is actually shrinking at the rate of 2 mm per second. 2 mm means that is 2 into 10 power minus 3 meter. Okay. So you can substitute all the known values and you can find out the value of the EMF, that is 3.25 microvolt. Okay. So that is the answer here. So now let us move on to question number 3. Okay, and this 3.25 microvolt is the answer, and it is option A. Okay, it is option A for second question. Now let us move on to question number 3. So here you have a conducting wheel. Okay, a conducting wheel in which there are 4 rods of length L is rotating with angular velocity omega in a uniform magnetic field B. The induced potential difference between the center and rim will be. You have the diagram and you have 4 options. Actually, what they are asking is you have a conducting wheel. Wheel means circular shape. Okay, like this. So this conducting wheel is having 4 rods of length L. Okay, it is having 4 rods of length L. That means this is one rod, Okay, and this is another rod, and this is another rod, and this is another rod. Okay, so here this is the conducting wheel, 4 rods of length L rotating with angular velocity omega in the uniform magnetic field. So circular loop is actually rotating. You need to find out the induced potential difference between its center and the rim. That means from here, okay. So actually, here you can see, okay, from this point. So from this point to this point, okay, between its center and the rim. So from this point to this point, what is the induced EMF? You need to find out. It is actually like a case. Okay, this is actually like a case. So once you find out the value of the induced EMF for this circular loop, you can apply the value as a formula or these type of problems. For similar type of problems, if you are given the value of the length or the radius of the circular loop, what you can do is you can use the formula. Okay, you can use the formula or you can use the answer which is derived from this case as the formula. So that formula can be used to find out the induced EMF between the center of the circular rod and any one of its end. Okay, any one of the point on the circle, you can find out the induced EMF. You can consider this problem as a case, and this one is actually the standard case from which you can apply the same formula for any similar type of problem. So you need to observe this thing carefully, because in that test, okay, in this test actually, I have given you similar type of problems, 2 or more similar type of problems based on this idea. Okay, so once you understand the solution for this problem, you can take the final result or the answer for this problem as the formula. You can use this as a formula and you can solve the similar type of problem. So here you see the into mark. Okay, the into mark shows the uniform magnetic field, and this conducting wheel, it is actually rotating. So how you are going to find out the induced EMF? You see here, from this point to any point on the circle, you need to find out the potential difference or EMF. For that, what you can do, the entire distance, okay, the entire distance is nothing but the length of the rod. So the entire length of the rod can be considered to be separated into portions of width dx. Okay, here you can see it is actually dx. So the entire length L of the rod can be separated into small portions, each of length dx. Okay, and from the center O, this dx is at a distance of x from O. Okay, you can consider it that way. That means the entire length of the rod is L. That has been given in the question itself. What you are doing is you have to separate the entire length into small portions of length dx each. And from the center O, okay, this dx is at a distance of x. Okay, so now we are going to find out the induced EMF between the ends. So for this small portion, what is the induced EMF? So that's why we are taking it as dE. Okay, for the small portion, what is the induced EMF? That is BLV. I think you know very well. Okay, so how I wrote this term on the right hand side of this equation, because E equal to BLV is one of the formulas. Okay, I think you know very well. We have discussed this also. So let me write it here. E equal to BLV. That means if you have a rod, okay, rod of length L, okay, rod of length L, moving with velocity v in a uniform magnetic field, then what is the induced EMF? Induced EMF is nothing but E equal to BLV. Okay, so based on this equation here, I am writing B, okay, as the magnetic field, and L is here actually the length of this element, okay, that is dx. Okay, instead of L, the length of the small element is dx, and here I have written omega x instead of L. Okay, omega x instead of L. And why I have written like that? Okay, because you know very well, okay, the velocity in circular motion, velocity of the motion is given by v equal to r omega. Okay, v equal to r omega. So that velocity here, you need the velocity term, okay, for the induced EMF. So this velocity can be considered as v equal to r omega, that is angular velocity into the radius. So here we are considering only the element dx. So the radius of the element dx is x. So v equal to radius into angular velocity in the formula. So here instead of v, I am using omega into x, that is x into omega, which is actually the velocity. So E equal to dLv, instead of we are writing v omega x dx. So after that, when you want to find out the EMF from this point to this point, what you have to do? You have to integrate this entire term. Okay, you have to integrate this entire term because right now we have found out only the EMF for this portion. When you want to find out the EMF for the entire portion, you need to integrate this. So while integration, you need to take the limits as 0 to p. Okay, so 0 to p means actually it is the length of the rod, because in the question they have given rods of length L. So 0 to L are the limits. So instead of dE, you need to substitute all these terms. Okay, you need to substitute b omega x dx, and here what are the variables? X. So b omega can be taken outside, and when you integrate x dx, that will be x squared by 2. So after integrating this x squared by 2, you can apply the limits L. So that is b omega L squared by 2. So this is the answer for this question, and of course this answer can be used to solve problems of similar type. Similar type means when you have a conducting circular coil or circular loop, when that conducting circular loop is moving in a magnetic field and you want to find out the EMF between the center of the circle and any point on the circle, okay, any point on the circle, the induced EMF between these two portions can be found out using this equation b omega L squared by 2. This is option D, and you should remember this formula. You can use this formula for any other similar type of problems. And the next question is graph based question. The current I in a coil varies with time as shown in the figure. The variation of induced EMF with time would be, okay. They have shown you the variation of current in the coil with respect to time. So here you can see from 0 to this point, okay, it is increasing. 0 to t by 4. T by 4 means it is actually 1/4 of the total time period. So from 0 to t by 4, the current is increasing like this. From t by 4 to t by 2, the current remains constant. And from t by 2 to 3t by 4, the current is decreasing. Okay, this is actually the variation of current with respect to time. And now what we have to do, we have to find out the variation of induced EMF with time. For that, you have been given 4 graphs, and among the 4 graphs, you need to find out the right one. Okay. So here you see, we have the formula E equal to minus L into di by dt. So why we have to use this formula? Because here they are asking us to find out the answer on the basis of this variation of current. So E equal to minus L into di by dt. Okay, E equal to minus d phi by dt, and phi is nothing but Li. I think you know very well. So I think I can write that also here. E is equal to minus d phi by dt. So instead of phi, what you can do? You can put Li. Okay, I think you know that very well. So you can take L outside, and it will be di by dt. This is E. Okay. So E equal to minus L into di by dt. That means the EMF depends on the variation of the current with respect to time. So in our question, from 0 to t by 4, okay, from 0 to t by 4, di by dt is positive. Okay, di by dt is positive. In that case, the EMF should be negative, because when this term is positive, your EMF is negative, because you have a negative sign in the equation itself. So from 0 to t by 4, di by dt is positive, so your EMF should be negative. And from t by 4 to t by 2, di by dt is 0. That's because here you can see the current is maintained at a constant value. Here you can see. The current is actually maintained at a constant value. That means di by dt equal to 0 for this region from t by 4 to t by 2. So for that case, you will be having di by dt 0. So your EMF will also be equal to 0. And from t by 2 to 3t by 4, your di by dt is negative. That means with the increase in the value of time, your current is decreasing. So here you can see. With the increase in time, the current is decreasing. So here di by dt is negative. That means EMF is positive. Okay. So all these things can be satisfied from option B. Okay. Initially positive, initially negative variation of EMF for this region, and then zero value of EMF for this region, and then positive value of EMF for t by 2 to 3t by 4. So that is option B actually. Okay, in option B you can see that variation. Okay, so that's why option B is the right answer. And question number 5: a coil of resistance 400 ohm is placed in a magnetic field. If the magnetic flux phi Weber linked with the coil varies with time t, as phi equal to 50 t squared by 4, then current in the coil at t equal to 2 seconds. Okay, a coil of resistance 400 ohm is placed in a magnetic field. They have given you the magnetic flux value, and you need to find out the value of current in the coil at t equal to 2 seconds. Current you need to find out. So they have given you resistance and magnetic flux. So what is the formula? I equal to E by R. That is the formula you need to use. Okay, I equal to E by R. For finding the EMF, you need to use minus d phi by dt. Okay, minus d phi by dt. So we need to find out the EMF value at t equal to 2 seconds. So here they have asked us to find out actually the current in the coil. So all the options are positive. Okay, all the answers are given in positive. So for induced EMF, you can actually neglect the sign here. Then only you will be getting positive value of current. Okay, because I equal to E by R. So here you can actually take the magnitude of the EMF at t equal to 2 seconds. For finding the EMF, that is d phi by dt, that means you have to differentiate phi with respect to time. So that will give you 100 t. Okay, 100 t when you differentiate this. So 100 into t equal to 2 seconds, that is 200. EMF equal to 200 volt, then I equal to E by R, that is 200 by 400, that will be 0.5 ampere. So that is option A from the question. And question number 60, you can see the current I in the inductance is varying with time according to the plot shown in figure. Okay, according to the plot shown in figure. So the variation of current with respect to time has been given for an inductance. We need to find out the correct variation of voltage with respect to time. Okay, voltage means that is the EMF, so or the voltage. So the variation of voltage with respect to time we need to find out. So for inductor, we know very well, as I have shown you, E equal to minus L into di by dt. So here L into di by dt. Okay, for t equal to 0 to t equal to t by capital T by 2, your di by dt is positive. Okay, because here you can see for the first case di by dt is positive. That means current is increasing for the first phase. Okay, so your potential difference, it is also L into positive, so that is positive. For the second phase, the current is actually falling down. So that means your potential difference is negative. So initial positive variation and then negative variation of potential difference can be observed. So that is shown in option D here. Okay, that is shown in option D here. Okay. Then question number 7. A wire loop is rotated in a magnetic field. The frequency of change of direction of the induced EMF is. Okay, the wire loop is actually rotated in a magnetic field. The frequency of change of direction of the induced EMF is. So answer is twice per revolution. How it is twice per revolution? Because you know very well, okay, when a coil is rotating in a magnetic field, as you can see from the AC generator concept, okay, in the AC generator, what is the pattern of variation of that induced EMF? So that is nothing but a sine wave. Okay, I think you all know very well about that. During the rotation of coil in AC generator, your EMF actually varies in a sinusoidal way. Okay, so this is one type of variation. Okay, change of direction, and then after one half cycle, you will be having second variation. Okay, so totally for one complete revolution. Okay, for one complete revolution, you will be having change in direction of the induced EMF 2 times per revolution. Okay, so when the coil in AC generator rotates, you can find out the frequency of change of direction of the induced EMF is 2 times during a revolution. So here also you have a similar scenario. So you have a wire loop rotated in a magnetic field. So the frequency of change of direction of the induced EMF is twice per revolution. That is option D. Okay. Then question number 8. A thin semicircular conducting ring PQR of radius R is falling with its plane vertical in a horizontal magnetic field B as shown in the figure. You can see a semicircular conducting ring of radius small r is falling with its plane vertical in the horizontal magnetic field as shown in the figure. The potential difference developed across the ring when its speed V is. Okay. And once again you have options. Okay, once again you have options. So you need to find out the correct option, and we need to find out the EMF. So EMF E equal to BLV. You know very well BLV. So BLV means here L is nothing but effective length. So the total length of this semicircular ring is actually 2 times the radius. That is diameter. Okay, diameter. So B into B into 2R. Okay, 2R into BV. This is the value of the induced EMF. Okay, and one more thing which you need to find out from the question is that here actually we have found out the induced EMF value, that is 2R BV. Okay, 2R BV, and in the option option D mentions you that the R is at higher potential. And of course, the induced EMF 2RBV is only there in option D, so you can straight away choose this answer. But you need to know why R is at higher potential. Okay, R is at higher potential is also given in the answer. So why this R is in higher potential, that you need to know. Okay, because here you see this into mark. Okay, this into mark shows you that the magnetic field is actually directed into the plane of the paper. Okay, when you see this diagram drawn on a paper, what does it mean? Okay, when you see into mark for the magnetic field, what does it mean? Because the magnetic field is directed into the plane of the paper. Okay, or when you see this diagram on your laptop or mobile screen, the magnetic field is directed into the plane of your screen. Okay, into the plane of the screen. It's not coming outside of your screen, or the magnetic field is not coming outside of your paper. So when the magnetic field direction is into the plane of this paper, from Fleming's right hand rule, okay, the induced current flowing in this coil is actually along the anti-clockwise direction. Okay, it's actually along the anti-clockwise direction. So the current flows from here to here. Okay, like this. This is the anti-clockwise direction. How did we get this direction? From Fleming's right hand rule. So current is flowing from this direction to this direction means R should be at higher potential. Okay, you know very well, in a battery, current flows from higher potential to lower potential. So here current is flowing from anti-clockwise direction means it is moving away from R and it is coming towards P. That means your R is at higher potential. Okay, so based on these things, you can conclude that option D is the right answer. And then next question is question number 9. A conducting square frame of side A and a long straight wire carrying current I are located in the same plane as shown in the figure. The frame moves to the right with a constant velocity v. The EMF induced in the frame will be proportional to. Here we don't have to find out the exact value of the induced EMF, but the proportionality relation we need to find out. Here in the question they have given you that a conducting square frame of side A and a long straight wire carrying current I are located in the same plane as shown in the figure. The frame moves to the right with a constant velocity v. Here you can see the frame is actually moving to the right with constant velocity v, and the side of this square frame is actually small letter a. Okay, and it is moving with a constant velocity v. The EMF induced in the frame will be proportional to. EMF means you need to find out the potential difference between this point and this point. Okay, that is the EMF induced in this frame. Okay, in this frame you can find out the potential difference between this point and this point. So that difference will give you the EMF, because here you are having empty space. Okay, here you are having empty space, so that doesn't count. So you need to find out the potential difference between this point and this point. So based on that, you need to find out the answer. So for this, option D is the right answer. How? Let us see. E equal to BLV. Okay, E equal to BLV is the formula which you need to use. L means the length of the frame. Here the length and the side of the square is same. So instead of L, you need to write small letter A. Okay, and V is the velocity. Here also V is the velocity. And this magnetic field, okay, difference you need to find out. B1 minus B2. B1 minus B2 means the magnetic field difference between this point and this point. I am considering as 1 and 2. So at this point, what is the magnetic field you need to find out? Because this point is actually closer to this current carrying wire. That means the magnetic field due to the current on this point is more actually, and when compared to this point. Because this point is far away from the current carrying wire. That means here the magnetic field due to the current flowing in the wire is actually less compared to this point. So difference in magnetic field between these 2 points is crucial to find out the answer. So here B1 minus B2. So due to the long wire, what is the value of the magnetic field? Okay, due to the long wire, what is the value of magnetic field? So that is actually, you know very well. I think we all might have studied about this concept in magnetic effects of current. Okay, when you have a straight wire, what is the magnetic field due to the straight wire? That is mu naught I divided by 2 pi into R. That means when you have your wire and here you have a point and you need to find out the magnetic field at this point. So this point is at a distance R from this wire. Okay. So then what is the value of magnetic field at this point? That is given by B equal to mu naught I by 2 pi R. So here at this point you need to find out the magnetic field, that is B1. Okay. That is B1, and at this point what is the magnetic field? That is B2. So when you want to find out the magnetic field at this point, mu naught I by 2 pi, so all these things are constant. R means the distance from the current carrying wire. So this point distance from this wire you need to find out. Okay, so this distance you need to find out. This distance is nothing but x minus a by 2. From this diagram you can find out this x minus this a by 2. Okay, this x minus this a by 2. A by 2 means this value. Okay, the whole distance is x, and when you subtract this a by 2, you will be getting this distance. So that thing we need to keep in mind. So here mu naught I by 2 pi into x minus a by 2 for this point, and for this point B2 is given by mu naught I by 2 pi into x plus a by 2. Okay. So here you need to find out mu naught I by 2 pi x minus a by 2 minus mu naught I by 2 pi into x plus a by 2. So when you simplify this, what you can do, you can take 2 pi as a common outside, then you will be having mu naught I by x minus a by 2 minus mu naught I by x plus a by 2. Okay. When you simplify this, then you will be getting this kind of relation proportional to 1 by 2x minus a into 2x plus a. So like that you can arrive at the solution. Option D is the right answer. This is how you need to find out. Then question number 10. A long solenoid has 1000 turns. When a current of 4 ampere flows through it, the magnetic flux linked with each turn of the solenoid is 4 into 10 power minus 3 Weber. The self-inductance of the solenoid is. So you have a long solenoid of 1000 turns. When a current of 4 ampere flows through it, the magnetic flux linked with each turn of the solenoid is 4 into 10 power minus 3 Weber. Self-inductance of the solenoid you need to find out. So the formula is N phi equal to Li. You need to find out L equal to N phi by I. N is 1000 turns. Phi is 4 into 10 power minus 3. Okay, that is Weber. Instead of phi, you can use 4 into 10 power minus 3 divided by I. I is the current. Current is nothing but 4 ampere. So L equal to 1 Henry. That is option C. Okay. Then question number 11. A uniform magnetic field is restricted within a region of radius small r. The magnetic field changes with time at a rate dB by dt. Loop 1 of radius capital R greater than small r encloses the region small r, and loop 2 of radius r is outside the region of magnetic field as shown in the figure. Then the EMF generated is. Okay. You need to find out the EMF generated here. What they are telling is a uniform magnetic field is restricted within a region of radius small r. So that you can see from the figure, the inner circle. Okay, the inner circle is actually having the magnetic field represented by these plus marks. So that inner circle is having the radius small r. Okay, so whatever magnetic field is here, the magnetic field is restricted within this inner circle. Okay, and this outer circle of radius capital R is actually encloses this inner circle. Okay, that means this outer circle can also have the magnetic flux from this inner circle linked with it. Okay, because this outer circle is actually encloses the inner circle of radius small r. But here you have another circular loop. Its radius is also capital R, but this is outside this concentric circles. That means this is not actually enclosing any magnetic field from this inner circle. Okay, it is actually outside the region of magnetic field. That means no magnetic field is linked with the second loop. Okay, the EMF generated they have asked. So from the 4 options, you need to choose the right one. Obviously, it should be 0 in loop 2, right? It should be 0 in loop 2 because loop 2 is actually outside the region of magnetic field. And if it is 0 in loop 2, okay, you have 3 options here. Option A, option C, and option D. Obviously, option A cannot be the answer because in loop 1, the EMF cannot be 0 because this loop 1 is enclosing the inner circle of magnetic field. So that means option A and option B are ruled out. So only thing is option C and option D you need to check and you need to find out which one is the right answer. So for that, EMF E equal to minus d phi by dt, that is minus d by dt into BA. BA means you can take A outside because area is constant and dB by dt. Okay, dB by dt. So EMF for first loop is minus pi capital R square because this is the area for the loop 1. So minus pi R squared into dB by dt is the EMF for loop 1. For loop 2 it is 0 because it is not enclosing any magnetic field. So this option is in option C. So minus pi R squared dB by dt in loop 1 and 0 in loop 2. So this is option C. Okay. And we shall move on to the next problem. That is question number 12. A long solenoid of diameter 0.1 meter has 2 into 10 power 4 turns per meter. At the center of the solenoid, a coil of 100 turns and radius 0.01 meter is placed with its axis coinciding with the solenoid axis. The current in the solenoid reduces at a constant rate to 0 ampere from 4 ampere in 0.05 seconds. If the resistance of the coil is 10 pi squared ohm, the total charge flowing through the coil during this time is. That means you have a solenoid, okay. At the center of the solenoid, you are having another coil of 100 turns and radius 0.01 meter. Okay. The current in the solenoid is actually reducing at a constant rate to 0 ampere from 4 ampere in 0.05 seconds. The resistance of the coil is 10 pi squared ohm. The total charge flowing through the coil during this time is. So you have a solenoid coil, okay. Inside the solenoid coil, you are having circular coil. So that means when current flowing through the solenoid changes, it will be giving some magnetic field, and since the coil inside the solenoid is placed in the magnetic field of solenoid, it will be having some EMF. Okay. Based on these concepts, we need to solve this problem. EMF E equal to I into capital R. So I is nothing but dq by dt into capital R. So E is nothing but d phi by dt. That is equal to, this is actually based on Ohm's law, E equal to IR. So instead of E, you need to put d phi by dt. This is equal to, instead of I, current is nothing but dq by dt into capital R. So you have resistance R given from the first thing, so that is 10 pi squared. So 10 pi squared. So we need to find out di by dt. Di by dt means the rate of change of current. Current is actually falling from 4 to 0 in 0.05 seconds. So di is 4 ampere, dt is 0.05 seconds. So what you have to find out is, you need to find out dq here. Okay, dq has been asked in the question. Okay, dq has been asked in the question. So the total charge of it is not actually dq, it is the total charge. So whenever you need to find out the total charge, the starting equation is dq by dt, and from this you can find out dq, and then you can integrate dq so that you can find out the total charge. So based on that approach, from this equation you can keep dq on one side and you can take all the other terms on other side. So that is dq equal to d phi by dt into dt into 1 by r. Okay. So here dt and dt will be cancelled out. D phi is actually the change of flux. So change of flux, I think you know the equation for a solenoid. That is mu naught n1 n2 a into di by dt. So that equation has been used here. Mu naught n1 n2 a into di by dt. That a is nothing but pi r square into di by dt into 1 by r. So dt and dt will be cancelled. You have di and r, and n1 and n2 you have the values. Okay, the number of turns in the solenoid and the coil. Of course, all the values you can substitute. You can find out the answer as 32 into 10 power minus 6 coulomb. That is 32 into 10 power minus 6 is nothing but 32 microcoulomb. Okay, right. So 32 microcoulomb is option C. And now we are going to move on to question number 13. The magnetic potential energy stored in a certain inductor is 25 millijoules when the current in the inductor is 60 milliampere. This inductor is of inductance. You have 4 options and you have been given magnetic potential energy stored in a certain inductor, that is 25 millijoules. And what is the value of inductance? So U equal to 25 millijoules, that is half Li squared is the formula which we know very well. Okay, energy stored in inductor, that is half Li squared, and from that we need to find out L. You can take all the terms other side. Okay, so here L equal to 2U by I squared. Instead of U, you can substitute the value given in the question, and I, you know very well, 60 milliampere, that's also given in the question. So you can simply substitute all the known values and find out the value of inductance. That is 13.89 Henry, option A. Okay. Now question number 14. The 800 turn coil of effective area 0.05 meter square is kept perpendicular to a magnetic field 5 into 10 power minus 5 Tesla. When the plane of the coil is rotated by 90 degree around any of its coplanar axis in 0.1 second, the EMF induced in the coil will be. So read the question carefully. A 800 turn coil of effective area 0.05 meter square is kept perpendicular to a magnetic field 5 into 10 power minus 5 Tesla. When the plane of the coil is rotated by 90 degree around any of its coplanar axis. Okay. So plane 800 turn coil is kept perpendicular to a magnetic field means the angle between the area vector and the magnetic field is 0 degree. Okay, initially. And now they are actually rotating it by 90 degree. Okay, in 0.1 seconds. What is the EMF induced in the coil? So change in magnetic flux by time will give you the EMF. So change in magnetic flux means here you see final flux is NBA cos 90 degree. So I think you know very well the equation for phi, that is NBA cos theta. Okay, in the second scenario, theta is 90 degree because it is rotated 90 degree, and initially it is the area vector is nothing but it is aligned at 0 degree. So NBA cos 90 degree minus NBA cos 0 degree. So here cos 90 is nothing but 0. So here NBA cos 0, that will be minus NBA. Cos 0 value is actually 1. Okay. So minus NBA. So you know all the values, 800 turns into B is nothing but 5 into 10 power minus 5 Tesla. And effective area they have given 0.05. So all these values you can substitute and find out the change in flux, that is minus 2 into 10 power minus 3 Weber. When you divide it by time, that is 0.1 seconds. Okay, question in the question they have given, so substitute the values, find out the EMF, that is 0.02 volt. Okay, so once again this is also a simple problem. Only thing is you need to understand the formula. Okay, formula and the little concepts. So option D, 0.02 volt. The next question is question number 15. It is a memory based question. Okay, once you are thorough with the theory concepts and the applications of eddy current, you can easily find out the answer. That is, in which of the following devices the eddy current effect is not used? Okay, you have 4 options: induction furnace, magnetic braking incline, electromagnet, and electric heater. So among all these options, where the eddy current is not used, that is option D, that is electric heater. Okay. So this is question number 15. Now we have question number 16. A wheel with 20 metallic spokes, each 1 meter long, is rotated with a speed of 120 RPM in a plane perpendicular to a magnetic field of 0.4 cos. The induced EMF between the axle and the rim of the wheel will be. Okay. So as I have told you earlier, okay, the similar problem has appeared here. Okay. Initially we saw a problem, actually that problem is a case. Okay, I told you earlier during this class. So similar type of problem. A wheel with 20 metallic spokes means it is nothing but a conducting circular coil. Okay, wheel means it is circular in shape, you know very well. With 20 metallic spokes, each of 1 meter long, rotated with a speed of 120 RPM in a plane perpendicular to a magnetic field of 0.4 cos. The induced EMF between the axle and the rim of the wheel will be. Okay, similar problem. Okay, similar problem. So here, this is the circular rim. Okay, so the induced EMF between axle and the rim. That means the axle is actually here. Here you have the axle. Okay. And you have 20 spokes. You can have any number of spokes, that doesn't matter. You need to find out the EMF between this part rim and the axle. That means the induced EMF between this part and this center. So this thing you need to find out. So induced EMF formula is E equal to B L squared omega by 2. So this formula you can use right away, but here omega is given in RPM, okay, revolution per minute. What you have to do is you have to convert this to radian per second, okay, because the SI unit of omega is radian per second. So E equal to B L squared omega by 2 is the formula which you need to use, but omega you need to convert it into radian per second. How you can do that? That is omega equal to 2 pi into n by 60. N means the RPM value. Okay, omega equal to 2 pi into n by 60. The RPM value is 120. So you can substitute these values and find out omega equal to 4 pi radian per second. This is the value of omega. And after finding this, you can substitute this in this equation. B L squared omega by 2. Here L is nothing but the length of the metallic spoke, that is 1 meter. So B L squared omega by 2. Here B is 0.4 Gauss. Okay, so Gauss means it is 10 power, you have to multiply that with 10 power minus 4 Tesla. So this is the conversion. This is also important. Okay, when your magnetic field is given in Gauss, what you have to do, you have to multiply that value with 10 power minus 4. Then you will be getting the magnetic field value in Tesla. Okay. So after finding it, you can substitute and find the you can find the answer for this problem. Okay, once you are done with this omega, okay, it is very easy. Okay, the same formula you can use. So the next question is the magnetic flux linked with a coil in Weber is given by the equation phi equal to 5p squared plus 3t plus 16. The magnitude of induced EMF in the coil at the 4th second will be. So they have given phi value. You need to find out the induced EMF at the 4th second. That means at t equal to 4 seconds, you need to find out the induced EMF. So what you can do is you have to find out E equal to minus d phi by dt. So here you have to differentiate this equation. After differentiating, you will be getting this thing 10t plus 3, because how will you differentiate? 5t squared plus 3t plus 16. When you differentiate, you will be getting 10t plus 3. So at t equal to 4 second means substitute t equal to 4 here, and then 10 into 4 plus 3. That will be giving you 43 volt. That is option C. Once again, very simple problem. Okay, option C, 43 volt. Then question number 18. A step-down transformer connected to an AC main supply of 220 volt is made to operate at 11 volt, 44 watt lamp. Ignoring power losses in the transformer, what is the current in the primary circuit? So here we need to apply the concepts of step-down transformer. A step-down transformer connected to an AC main supply of 220 volt is made to operate at 11 volt, 44 watt lamp. That means that AC main supply is the primary coil and that lamp is actually the secondary coil. So what is the current in the primary circuit? We need to find out. So here they have asked us to ignore the power losses. That means your input power should be equal to the output power. Input power means power P equal to VI. V means potential difference or EMF. So input power means current in primary circuit, IP into EP equal to IS into ES. Okay, this is the output power. From here, what is the current in the primary circuit? That has been asked. So IP equal to IS ES by EP. Okay, from this equation you can write down. So IS is the current in secondary coil, but we don't need IS separately. It is actually the output power, right? IS into ES is the output power. So output power means here 44 watt lamp. That is the output you need. So you can substitute 44 watt in place of IS ES divided by EP. EP is the EMF in the primary circuit. EMF in the primary circuit is 220 volt. So you can substitute that 44 by 220, that will be 0.2 ampere. That is the current in the primary circuit, and that is option E. Okay. And now we are moving on to question number 19. two conducting circular loops of radii R1 and R2 are placed in the same plane with their centers coinciding. If R1 greater than R2, the mutual inductance M between them will be directly proportional to. Okay, you have two circular loops. So two circular loops with their centers coinciding. You need to find out the mutual inductance. So phi equal to Mi is the formula. Okay, phi equal to Mi is the formula. Phi, how you can find out? For a circular coil, the phi value is given by mu naught I by 2R. So here, the outer loop is having the radius R1. Okay. So due to the outer loop, you will be having the inductance in inner loop. So for the outer loop, you will be having this much of magnetic field mu naught I by 2R1 at the center. And phi equal to BA is the equation. And A is nothing but area of the inner coil, that is phi R2 square. So mu naught I by 2R1. This is the magnetic field due to the outer loop, and this B should be multiplied with the area of the inner loop. Okay, that is phi R2 square. R2 is the radius of the inner loop. So you have got phi, and you need to find out the mutual inductance. So for that you need to use this equation. Phi equal to Mi, that means M equal to phi by I. So pi by I means you need to divide this equation by I. So when you divide this, your I will be cancelled, and we need to know the proportionality relation alone, that is R2 squared by R1. Okay. I think you understand this problem very well, and we have discussed up to question number 19, and we shall stop with this. Okay, and we will be discussing the solutions for remaining problems in our next class. Thank you so much for joining the session. Thank you.
Thank you, sir.